So maybe I'll say aspects of proof. Okay, so kind of step one is to do the linear theory. Okay, and the idea is that we have kind of the first thing we do when we look at this. So this is all about this operator h hat, which is sort of this funny elliptic operator. So the first thing we do is we prove integrated local energy decay. Okay, and this is kind of maybe you should so sort of our kind of so we kind of using spectral methods, using spectral information. Okay, and so this is the point is we have this variable coefficient operator, and sort of this is a weak form of dispersion, which is one way to sort of start looking at dispersion. And this is sort of inspired by kind of these works of Tataru and collaborators. Okay, in particular, there's this kind of work 08. There's kind of more works here. Okay, the second thing is then to try to sort of upgrade this to pointwise decay, and for this we use this RP method of Defermos-Roniansky. And then there's this modification for inverse square weights. And so I think here there's this paper of Gaik. Okay, and the point is sort of these are kind of some robust tools that have been developed to kind of justify the statement that we have convergence to a radiation field. Okay, maybe actually I want more space, so I'll move back over here. Or maybe I'll just kind of stick near here. So a very quick kind of comment on the nonlinear part. It's a nonlinear argument. Okay, so for this, we first kind of pick T1 so that there is linear dispersion, convergence to radiation field. And so y in here. So there's some time T1 that depends on the initial profile, but is independent of epsilon. So that okay, at this point, you expect your solution, at least at the linear level, to be close to the radiation field. So this is sort of region A. In region A, you use linear theory. And like epsilon being small to close. Okay, and then so then sort of at least for a linear wave equation, you expect that your solution at this point will be sort of from then on concentrated in this outgoing light cone from the origin. And so I'm going to split kind of so. Okay, now there's this other time t equals of epsilon to the -2/5. Okay, that's regions B, C, and D. So for region B, I think the idea is to use something related to finite speed of propagation. I'm putting quotes here because, first of all, Euler-Poisson is a non-local system. This operator we wrote down over here is local, so that sort of suggests that the non-locality is not so important, at least at this kind of this part of the argument. It's important for showing the existence of the steady state with this nice decay rate at infinity, but sort of the rest of the contributions will end up being sort of lower order. Maybe another reason why we can't just say finite speed of propagation is that we also need to do a modulation. And so, okay, that could also sort of break finite speed of propagation, at least if you just kind of say it in the most explicit way. But the idea is that, okay, you should expect things are small here if you start very concentrated to the origin. In method C, in this case, so we use the successful method of geometric coordinates, pioneered by Christodoulou. And here we integrate along characteristics. Okay, and as maybe another comment, we kind of deal with the inverse square interaction. So maybe one kind of difference between this case and just the case that I raised with the 3D wave equations. That for 3D wave equation, you really have that once you multiply R, you have transport equations of radial symmetry. But here, okay, there is some like 1 over R term, but okay, part of what we do is we sort of take care of this term. And then region D, so here, the idea is to use, so I guess peeling properties. Of the wave equation. Okay, and so actually this is another sort of thing that we show at the linear level, is that sort of, okay, for the normal wave equation, you expect that your solution will just be concentrated here, but we know that for other wave equations, we should still have some sort of decay as you go inside the light cone, and so that's something we have to show, but the point is that this is what's going to sort of stop anything bad from going here, but you also need to modulate to get rid of the linear instability. So I should make a comment that, okay, sort of the initial data that we're considering this problem is sort of kind of very close, so sort of very close to the space. And so you're going to have to sort of pick your modulation parameters to avoid triggering this. But yeah, I think I'm over time, so I'll stop. Thanks for listening.
Hope you enjoyed the coffee. It's my great pleasure to have Mahir Hadzic from University College of London, who made the long trip overseas to tell us about stable radial implosions for self-gravitating fluids. Take it away, please.
Thank you very much. This is my first time here. Thank you. It's lovely. My voice, my voice has gone a little bit, so it's like it's one of the things that's being modulated today. So yeah, bear with me. Hopefully it survives. Everything I'll talk about today is based on these works on a sequence of works with Yang Guo, Juhi Zhang, and Matthew Schrecker. And part of the intention today is to explain what these words in the title actually mean. In particular, what I mean by implosion, and what does the word self-gravitating refer to. After an introduction, I'll do a bit of an overview because I announced it in the abstract, and then focus on some of the developments in this area. And finally, if time permits, I'll do something slightly more technical at the very end. So luckily, Eli gave us a nice introduction. So when I say a star, and this talk is sort of rooted in, say, astrophysics, very sort of broadly speaking, when I say a star, I mean a self-gravitating gas, which means that you take Euler equation and you couple it to gravity. And if you are, and then it's up to you whether you want to describe gravity by Newtonian or by relativistic theory. Okay. It turns out I will mention both in today's talk. So that being said, this is exactly the same model that Eli wrote down in the previous talk. Rho is the density, U is the velocity. They satisfy the continuity and the momentum conservation law. And very importantly, the Poisson equation, which in this case describes coupling of the fluid gas to the gravity, is equipped with a boundary condition. And that boundary condition states effectively that this is an isolated star. Or in the language of GR, you would call this an asymptotic flatness assumption. And this is important because it also tells you that, for example, in the language of the previous talk, that you have to consider inhomogeneous, spatially inhomogeneous objects, because otherwise this wouldn't be compatible with the assumption of asymptotic flatness. Okay. shortly, I'll give you kind of a cheat sheet how to think of the momentum conservation law, because it expresses the balance of sort of three dominant forces in the problem: the inertia, the pressure, and the gravitational force. And you notice that I'm also using this index gamma, which is to suggest, just like in the previous talk, that this is a natural criticality parameter in the problem. So before I tell you what I actually am going to talk about, which is this first bullet point here, stellar collapse, let me tell you about other things that one might want to talk about. Okay, so the types of dynamical questions that you can ask in this setting is sort of numerous things. For example, you can entertain structures that expand. So this leads to some notion of dispersion. And this method physically might be related to something like, say, supernova explosions. You could entertain questions like the n-body problem, specifically when n is equal to 2. So the talk today, both this talk and the previous talk, n is equal to 1. But if you imagine having two self-gravitating bodies of fluid, tidal forces will kick in and they inevitably start deforming the supports of each of the two bits. And understanding sort of anything beyond, say, local existence is an interesting question. One of the open questions in this area is the question of existence of periodic or quasi-periodic structures. Very little is known. I think nothing at the nonlinear level. But we certainly observe these things. You can certainly see pulsating objects. You could also be less ambitious, and you can replace this by the question of constructing sort of long-lived, periodic-looking objects or structures. It's still an open question. And then finally, I'll get to this today in just a little bit, and Eli also got to it in a way in his previous talk. These questions of so-called criticality naturally have a very natural sort of this is a very natural platform to talk about criticality, which is something which is to be distinguished from the scaling criticality that was discussed earlier. So I'll touch on that a little bit later. Okay, but everything I really want to talk about today, or mostly, is this question of how do we understand stellar collapse? What does that even mean? So to kill the suspense, stellar collapse just means blow up of density. Sort of you start with smooth data, and then at some point density blows up. So some people like to call this implosion. And if nothing else occurs, no breakdown of regularity before that final moment of blow up, you call that smooth implosion, if you wish. So what's going on in this problem? I mentioned the cheat sheet. That is a good way to think of the problem is as a balance of these three forces: gravity, pressure, and inertia. And you can think of pressure as a defocusing feature of the problem, and then gravity likes to push things in. So a lot of the interesting stuff that happens here has to do precisely with this interaction. And then you can think of scaling of this parameter gamma. It allows us to distinguish supercritical and subcritical regimes in very much the same way as Eli pointed out in the previous talk. So a lot of what I'm going to talk about is going to reflect this kind of paradigm here. And let me throw out some big words on this slide. I didn't come up with them, and it's a hypothesis in the sense of physics literature. So it's something you can find there. And there's this claim that floats around that says that on approach to singularity, to sort of imploding stars, these solutions should look to the leading order self-similar, whatever that means. And if you want some references, you can find it in sort of various places. But one sort of way to interpret the word generically is to talk about stability. So this literature also insists on this type of model behavior, at least in radial symmetry, being stable. And the emphasis is on stable rather than finite codimension stable. Okay, so that's another kind of motivator for this discussion today. And then in GR, if you sort of want to describe genuinely relativistic stars, a similar picture exists. It goes back to works of Ori and Piran that states that sort of one should be able to find imploding objects or collapsing stars that exhibit some form of stability. Now, the way I like to think of it is that self-similarity is sort of a useful tool in finding interesting solutions. It's in particular, in GR, it's incredibly effective when you want to talk about particular type of singularities called the naked singularities that I'll mention later. So I can breeze through this because Eli already did it. When you get a new equation, you check the scaling invariances and conservation laws. This is the same scaling invariance that Eli wrote down in the previous talk. And there's nothing memorable, sort of, you don't have to look at the indices, you just have to know it exists. And if you sort of ask the question, what do the mass and the energy do with respect to this scaling, the answer is this one. Sorry, what am I doing? When gamma is 4/3, the mass is preserved by the scaling, and when it's 6/5, it's the energy is preserved by the scaling, as you saw in the previous talk. And then one thing that is perhaps worthwhile pointing out, unlike pure Euler, there's only one scaling. Once you fix a gamma, you have fixed the only invariant scaling in the problem. Okay. A way to think about this is that gravity or the presence of gravitational forces fixes the choice of scaling, and there's no freedom there to mess around with that. So let me just go back a slide. So in particular, these exponents, much like in the discussion of stability of Lane-Emden stars, they also play a role in the discussion of existence of, say, imploding structures, which is what I'm after. So this being sort of an overview talk, I want to give you a little bit of the, I want to say something about the literature. So in sort of mass critical case, critical things can happen. And as Eli pointed out, you can entertain sort of a separation of variables ansatz, which ends up working out. And this goes back to this astrophysics paper of Goldreich and Weber from 1980. So what they did is precisely this. You sort of make a modulation ansatz for your solution, where sigma is some profile to be found, and you plug it back into the equation, and you see that things separate beautifully. And so what you observe here that density is basically just a modulation of some profile to be found, and the velocity is an example of what is known as an affine flow. It's just sort of expanding. Sorry, it's proportional to R, so it's either expanding or contracting. And the answer is the modulation parameter lambda will solve an ODE to make this consistent. You can solve the ODE, and it's either going to expand and live forever or contract and blow up in finite time. Both scenarios are possible. So as a side note, there are results jointly with Juhi and the follow-up with King-Ming Lam, where we show stability of these solutions in the expanding direction. Not much is known about the behavior in the collapsing direction, for example. You can compute these rates and so on. Now, maybe it's good to keep this in mind. So gamma can be bigger than 4/3, equal to 4/3, and less than 4/3. And this is the subcritical regime here. Okay, this is the critical, and then we will call this supercritical. In the subcritical case, you cannot have collapse by density concentration. And this is believable. This is sort of a virial type argument. This goes back to like early aughts, right? On the other hand, you could say, well, what do we know about a global well-posedness for this problem? Well, I just told you that things can blow up and so on. Nevertheless, at least in radial symmetry, you can produce globally well-defined weak solutions. And this goes back to this work of Chen, He, Wang, and Yuan. And you notice even in this theory, the value of gamma with, and in its relation with respect to the two criticality exponents is important. Okay. So that sort of concerns briefly this discussion around subcritical and the critical case. So the question you want to ask, what happens if I go supercritical, namely gamma below 4/3? That's kind of the question. So a first result in this direction goes to a joint work with Yan Guo and Juhi Zhang from a while back now. And this is an example of smooth implosion, which is not self-similar. So the word that people in dispersive community like to use is type 2, which simply means not self-similar in this case, okay? And what you can do, you can prescribe a surface in space-time. Okay, this is all radially symmetric, and find solutions that exhibit blow up exactly along this surface. So this is kind of the maximal development of these data. You can prepare the data to live on a compact interval or infinite interval, that doesn't matter. Okay, in the language of sort of dispersive semi-linear PDE, this often goes to this so-called ODE blow-up mechanism. Yeah. It's a whole curve, absolutely, yeah. So you can construct such examples. There is no claim of stability of such examples, but they exist, yeah. So that's one possible model behavior, but the reason why these things exist, they are in some sense, if correctly interpreted, is designed as perturbations of the model dust collapse. So dust is the same problem, but without the pressure. And in that case, there is a sort of a well-known family going back 100 years ago of Stallman and Volkov and Oppenheimer of objects that exhibit collapse in finite time. And they are of the ODE type. And these are, even though these solve the problem with pressure, there's a regime within which you can treat the dust-like collapse as a model for the pressurized collapse. Okay, so the challenge is sort of having pressure in this model. So what about other implosion mechanisms? So what is there something that is likelier to be more stable? And so if you ask this question for any PDE, you sort of want to hope to put all the forces in balance within that PDE. A natural way of doing that is to probe for self-similar solutions, because that's exactly what they do. So let me sort of take us a step back and discuss the physics literature on this in this regard. So in the late 60s, Penston and Larson sort of independently, they made sort of this was sort of a big result for the astrophysics community. They discovered numerically self-similar solutions in the case when gamma is 1. Okay, sort of isothermal fluid. They discovered these self-similar solutions that exactly conform to that picture I mentioned before. That you start off smooth, and in finite time, the density blows up. And the blow up is sort of self-similar. Now, it gets kind of interesting because about 10 years later, Hunter realized that these solutions that Larson and Penston found, they sort of, one can think of them as kind of likely ground states of a discrete family of other imploding solutions that seem to get progressively more unstable as you move along this sequence, whatever the parameter may be. I'll maybe say a word about this later. And then further kind of insight came sort of 80s and the 90s through the works of Ori Piran and these other physicists that suggested that this Larsen-Penston collapse that we see up there should be sort of stable, whatever that means. And this lends credibility to the claim that one should think of it as kind of a ground state in some kind of family of solutions. So one of the questions is, can one actually construct these things? Like I said, gamma is 1 in this discussion. You might complain about that. So follow-up work by Yahiel gave, again, numerical evidence that the analogs of these structures actually exist even when gamma is bigger than 1. So for, let's say, if you care about Newtonian gravity, this may be a more realistic choice of an exponent. And also what physicists realized is that in this discussion, the smoothness that I referred to actually matters. So kind of the link between smoothness of these structures and stability was in some sense recognized in these works. And when I say smoothness, I really mean it in the language of, you know, taking derivatives and so on. Okay, so what are the rigorous results on this self-similar implosion for the self-gravitating fluids? So the existence of this Larsen-Penston collapse, this is a joint work with Yan Guo and Juhi Zhang from some while ago. Like I said, this is limited to the case gamma equals 1, the isothermal fluid. A much harder sort of range of exponents is the one when gamma is activated, when it's bigger than 1. So this is a joint work with the other 2 authors I mentioned and Matthew Schrecker. Why does this get harder? I'm not sure I'll have time to explain, but it is sort of there's sort of a lot more work here than here, and there's already, to us at least, there was already quite some work in this result as well. And so these first 2 results are references to what I would like to think of as ground state profiles of some kind. Fix a gamma, and then this is what you would hope is somehow stable. But you could ask the questions about this other end of the Hunter sequence that I mentioned earlier. And so there's these 2 very, very nice works by Eli. Let's call him Sandin for the purpose of this talk, where he shows existence of these highly oscillatory structures. So for large values of that parameter, when gamma is 1 and when gamma is bigger than 1. Okay. What about the relativistic analog of this problem? So this is a result from a few years back. So one can ask the question, by the way, I did not introduce the Euler-Einstein system, but if you ask me what it is, the correct answer is it is exactly what you imagine it to be, right? It's the coupling of Euler to Einstein. And so in this work, we prove the existence of the relativistic analog of the Larsen-Penston solution, which comes with sort of an interesting feature. Okay, it implodes, and this type of implosion triggers some kind of gravitational blowup, curvature blowup. And this singularity that arises has the interpretation of a so-called naked singularity. And interestingly, so naked singularity, I'll define it later, but for the moment, it's something that distance observers can see, okay? And it features a smooth Cauchy horizon. In fact, both of the characteristic lines, the backward light cone and the future light cone are smooth. There's nothing wrong going on across these surfaces. Now, okay, I'm talking about coupling to gravity. What happens if you, I should mention at the very least something about the body of work on this topic without gravity. So if you just focus on smooth implosion for Euler, then a lot of work has been done in recent years, triggered by this breakthrough result of Merrill, Raphael, Rodnyansky, and Sheftel from 2019. That's when it appeared on the archive, which led to a number of follow-up works. And what they prove is the existence of smooth implosion profiles in the sense that I explained for just Euler. And they prove sort of finite codimension stability. What this codimension is a separate question, and it's very likely bigger than 0, but that's a separate topic. I'll try to compare, or at least give you a sense of, even in the construction bit, what are the key conceptual differences between working with gravity and not working with gravity, and they are there. But we'll come to that in perhaps a few slides. Also, everything I mentioned in this slide is a discussion of isentropic fluids. So entropy is fixed, it's a constant. You could ask what happens if you turn on the entropy. Can you find sort of genuinely non-isentropic models of self-similar blowup? And the answer is yes. So such an implosion profile was constructed in a joint work with Christopher, who is in the audience, and Matthew Schrecker. And this implosion profile has this funny feature that the density blows up, but the pressure is 0 at the origin, which means that, okay, the only way you can accommodate for that if something non-trivial happens with the entropy. Okay, and just last week, a similar profile was constructed for Euler without gravity, and both results have this sort of undesirable feature that the pressure is in fact 0 at the origin. Okay, but such things exist. And I think, as far as the overview is concerned, I think I wanna not say much more and focus on what the results are that I want to discuss today. So I want to discuss how existence is shown of these self-similar profiles. In particular, I want to say a few things about this Larsen-Penstone profile and its gamma bigger than 1 analog. In fact, I will only talk about this construction because it's easier to present. And its relativistic cousin, the relativistic Larsen-Penstone solutions. I'm not sure that I'll have time to actually explain the construction of these self-similar solutions, but a lot of the ideas that go into this construction of the Larsen-Penstone, they sort of survive in some form in the other two works. Although this work here requires a considerable additional work with respect to the Newtonian case. So that's theorem 1. It has to do with existence. Now you could ask, can I say something about the stability of these objects? And that would be theorem 2. And theorem 2 is a recent work with Yang Guo, Juhi Zhang, and Matthew Schrecker, where we prove nonlinear stability of the Larsen-Penstone profile, which against radial perturbations, which is sort of, again, a way of reassuring you that there is a meaning to the words, this is a ground state object. And it's also an example of a stable, smooth implosion, which is sort of a good way to think about it. So what are the results? Existence and stability. Let me say a few words about existence first, before I can say anything about the stability. I find it a sort of fascinating topic, in particular because you have to deal with ODEs, which is very easy to, it's very easy to assume that your life's going to be good. Turns out this is the hardest part of a lot of these theorems, is precisely the ODE part. And I want to explain to you why. So for simplicity, from now on, gamma is 1. Okay, so the fluid is isothermal. Pressure is rho, P equals rho. Okay. I told you before there is a scaling invariance. In fact, Eli told you before there's a scaling invariance. So the right thing to do to look for a self-similar solution is to apply the correct scaling, which is this one here, when gamma is 1. And then you change variables, honoring whatever the scaling invariance you have. And you see it here. If you are able to find rho tilde and u tilde, which are now functions of this self-similar variable that are smooth or regular, then you have blow up of the original density, because if you start at time -1 and you reach time 0, something is blowing up. Okay, that's the idea. What does this self-similar variable actually mean? It's worthwhile thinking about it geometrically. These are rays. So when you fix a y, you're considering a ray that's emanating out of the origin. Y is 0 precisely at the center, and y sort of goes up to infinity at this line here. If you wanted to entertain the possibility of crossing over to the future, so when t is bigger than 0, then y will flip sign. Of course, you would have to make sense of what does it mean to go beyond y equals infinity. You don't have to, but it turns out you kind of have to think about this if you want to understand the relativistic version of this problem. Okay, so that's the geometric meaning. What will happen, you know this, because this is coming out of self-similar ansatz, you will get some ODE system for rho tilde and u tilde. And that ODE system is going to be a 2x2 system for the density and velocity. And it turns out it's non-autonomous. Okay, if this were Euler, it would be autonomous. Now, I do this just for the sake of accuracy. You don't really work with u. You work with sort of this relative velocity that I call omega. Physicists will call this wind velocity. And from now on, I shall refer to omega as the velocity, okay? And here is the promised 2x2 system of ODE. Now, I don't expect you to gain any intuition by staring at this system of ODE, but one thing you should notice is that there are these denominators. And when you see denominators, you worry if they could vanish or not. And that is precisely the question I want to ask. If I have a meaningful solution of this ODE system, which is smooth, is it true in any way that I have to contend with the possibility that the denominators vanish? And the answer will, of course, be yes. And I will explain to you in a second why. There is this hyperlink to the case gamma equal 1, but trust me, you don't want to see it. So you can do something very simple. You can Taylor expand at 0 and at infinity. If you have a smooth solution to this, omega, just by requirement of regularity, has to be 1/3 at the origin. And then you can play around with Taylor expansions a little bit more, and you can convince yourself that omega has to be 1 at infinity. So then, by the intermediate value theorem, 1 minus y squared omega of y squared is 1 at the origin and negative infinity at infinity. Therefore, there is at least one such point. This is a slope in the physical space where this thing vanishes. We give it a name. We call it a sonic point. And what does it actually represent? It's the boundary of the backward sound cone that emanates from the origin. And if you're too triggered by the word sound, think light, okay? So the definition of the sonic point is precisely the vanishing of this denominator, okay? And what I just showed you is that there has to be such a point. If you want to construct a smooth solution, there better be such a point. In principle, there could be more than one, but in the solutions that we construct, there is exactly one. And here is a slightly more precise version of the main theorem on existence when gamma is 1. So indeed, there exists a smooth solution to that ODE system. It's not just smooth, it's a real analytic. And it has a single sonic point. So there's a single value of y star where the denominator vanishes. The density is positive, and the velocity omega is indeed squished between 1/3, which is the boundary value at 0, and 1, the boundary value at infinity. What does it mean for the original velocity, the physical velocity? It turns out that this requirement here in particular implies that the original velocity is negative, which is meaningful because it's telling you that the flow is moving inwards. So kind of information is pushed towards the origin. And you can say something about the tail behavior of the density, which is that of 1 over y squared. In particular, in 3D, this means that these self-similar structures do not have finite mass. So kind of the tails are kind of fat. I'll just say it in passing. Similar statement, but harder result for the polytropes is also true. And this is a joint work with Matthew. We call them Yahil solutions because Yahil was the astrophysicist who entertained the possibility that they exist for gamma bigger than 1. And I will not say anything about them for the rest of the talk. So I want to give you a sense of how a proof of this might work. Before I do that, let me again go back to this a beautiful paper of Mel, Raphael, Rodnyansky, and Sheftel. Two conceptual differences that you can think that you immediately should strike you is that Euler has this 2-parameter family of invariances where this problem does not. You choose a gamma and the rest, everything else is prescribed, all the exponents. So, and the second one is that it is not an autonomous system of ODE, which in practical terms means that certain tools you are accustomed to about sort of 2x2 systems cannot be used in this setting. Okay, you have to entertain slightly different approach to things like existence and so on. So again, another way to think about it is, and I said it earlier, is that gravity fixes the self-similarity exponents. So how does the proof of this actually work? How do we solve that ODE? It's got 3 parts. For those of you familiar with kinetic theory, you'll notice that I nicked the terminology from somewhere else. And the 3 steps are the following. So the sonic point, if you remember, is a solution of some kind of equation where omega depends on the unknown. So I don't know where it is. So part of the problem is to figure out where the sonic point is. It depends on the solution itself. So it's got that free boundary flavor, okay? So what we do first, we identify we identify kind of a range of possible, let's say, meaningful choices for what I want to call the sonic point, this line y star. And then that's the ugly bit. And then we go straight to the hard part of the problem, which is to identify a choice for which I can actually solve the problem from here all the way in the interior to the center. Turns out solving from here to the other way is the good part, and because equation is much more stable in that direction. So let me actually say a few things about that. Let me not keep it at this sort of level of generality. So this is the step 1. After some thinking and browsing the literature, the correct educated guess for where you should look for this sonic point turns out to be this interval between 2 and 3, okay? Trust me. Having done that, I want to say the following. For any choice of this slope between 2 and 3, I can prove a local existence result a little bit to the left and a little bit to the right. So not until the recent work of Eli has there been a statement in the literature that actually tells you you can do this in general. It's not the case that it fits in the framework in an ODE textbook. So the way we do it, you write down the formal expansion for the, you write down the formal expansion around this putative sonic point, which you remember is makes the some denominator vanish. So if you want to have a smooth solution, the numerator better vanish at the as well at the same point. And this creates a hierarchy of consistency relations that you then have to satisfy. So you write that down, and you write some sort of recursion for rho n and omega n. And the goal is to prove that this thing converges. So if you want to sound fancy, this is sort of a combinatorial argument, and hence the justifying the terminology ugly. It's a lot of work. Yeah. Having done that, having sort of developed a local well-Poisonist theory off of like any of the slopes here, it turns out for most solutions, you will not exist, won't be able to connect all the way to the origin. And this is this so-called Friedman connection problem. It's bad naming. It could mean different things. So here we really rely on nonlinear invariances of the problem. We really have to exploit them. And the way this works is through some sort of a no return property. So I mentioned that the choice of y of the slope is somewhere between 2 and 3. And the meaning of those numbers is the following. If I start off very close to value 3, if I believe my sonic point is here, I can show that the velocity has to dip below a certain value, which is 1/3 in this case, and can't come back. That's kind of the ODE part of the statement. You dip below, you don't come back. And if you start off very close to 2, you can show that solution never dips below 1/3. And to have a solution, I have to reach 1/3 my boundary value at y equals 0. So you can now imagine a shooting type argument that will tell you that you can identify the sonic point as the first value coming off from 3 going left, for which the dipping doesn't happen. That's in fact how we define the sonic point. Okay, that's sort of believable when written like this. And then the easier part of this whole argument is to, for that particular value of y, let's call it y star, somewhere between 2 and 3, is to connect the solution all the way to y equals infinity. It turns out the ODE flow is very stable in that direction. So this is sort of not terribly hard. That connection works for any of these slopes between 2 and 3. So the picture is basically like that, if you want to draw a comparison to the previous picture. Any choice connects to infinity. Okay. And now you glue them together, and that particular one choice of y star, that is your sonic point, and that essentially is the core of the argument. I better go back. Okay. What is this link to criticality theory? Again, Larsen-Penston should be thought of as a ground state, and conjecturally, there is this sequence of sort of ever so progressively more unstable so-called Hunter solutions. And Eli proved their existence using sort of ideas from, some ideas from the dispersive world and sort of very sophisticated implicit function theorems that allow you to do that. How should you think of this parameter n? I mentioned that the ground state, the flow is ingoing. So u has a sign, velocity is negative. You should think of, loosely speaking, you should think of n as kind of the number of islands of positive velocity in an otherwise ingoing flow. That's kind of like a one way to interpret that. What about the relativistic case? So I'll state the result, but perhaps I won't talk about the existence because then I won't have to talk about the punchline. I won't have time to talk about the punchline of this talk. But what I want to say is the following. So if you couple Einstein in, say, radial symmetry to Euler, this is the Einstein equation. And on the right-hand side, you see the energy momentum tensor associated with the fluid. The question is, can you find similarly imploding solutions? If you are coming more from the fluids background, and if you're wondering where did the fluids equation disappear, they're encoded in these Bianchi identities here. They tell you that there are 4 propagation equations, which loosely speaking correspond to the 4 equations that we saw earlier for the Newtonian self-gravitating fluid. Now, let me go back. This equation is not closed as written because I have to tell you how pressure relates to density. If you want to study relativistic collapse, this is sort of most natural equation of state. Why? Because it honors the causality. Okay, if you wanted something like P equals rho to the gamma, that would violate causality at high densities. Okay, so epsilon here is sound of speed squared. Maybe an awkward letter to use for sound of speed, but it gives you subconsciously a hint that at some point epsilon will be small. If you turn off pressure, you get Einstein dust system, okay? And one other feature of this particular choice of equation of state is that it's compatible with invariant scaling in the problem. So you can run the same sort of scaling analysis. And moreover, if you knew that somehow the density blows up, so that's the implosion blow up, you would infer from a sort of by contracting the Einstein equations that the curvature also blows up. So it really does correspond to some kind of geometric blow up. So let's talk about dust, because it's an interesting story and kind of gives a nice intro to what I want to say. So dust Einstein equations are very well known, and going all the way back to works of Lemaitre and Tolman, people knew about solutions. They're essentially ODEs when written down in co-moving coordinates. So they were found in the 30s, but what Oppenheimer and Snyder did, they zeroed in on a particular subclass of those solutions where the initial density is basically homogeneous. And if you do that, you can really compute everything about this. And in particular, you can study the causal structure of the space-time. And that led them to this notion of what we now call a black hole. A twist to that story is that if you now zero in on the rest of those dust collapsing solutions that Tolman and Lemaitre had found, the ones that are not necessarily homogeneous at the origin, so they don't look like flat, you realize that the Oppenheimer-Snyder story is sort of exceptional in this broader class of solutions. And they generically, in fact, these singularities are generically not encapsulated in an event horizon, but instead lead to so-called naked singularities. So this is a significant gap in terms of like the years past. What is a naked singularity? This is the formal definition, but what it really means is that the future null infinity is sort of cut off. The distant observers can actually receive signals. And this is a handy definition that is phrased in terms of the affine length of the ingoing signals sent along some outgoing regular code. This is sort of telling you that you can't escape it. You cannot not see it, no matter how far out you go. Okay. So a work that influenced us profoundly is this beautiful physics paper of Ori and Piran. It's not just a numerical work, but there's a lot of insight there. And they sort of observed that these analogs of Larson-Penston solutions also exist in this context. And if you ask me in 3+1 dimensions what other naked singularity solutions are known, other than the dust that I mentioned and the stuff that I'm going to talk about, I'm aware of these two. So this is a well-known solution of Christodoulou of Einstein's scalar field, and then and then in vacuum, so necessarily therefore not radially symmetric, the work of Rodniansky and Schlapperton-Grothman. Both of these classes of solutions are not smooth in the sense that I'm talking. So there is always some kind of a failure of regularity along the backward light cone. So one interesting thing about these naked singularities of that Orient-Piran conjecture and that we construct is that they're actually smooth across the backward light cone. Now I'm gonna write down some equations because you might feel, I don't know, maybe you want to see them. Don't read into them too much, but they exist. We choose to work with co-moving coordinates. And one thing perhaps to remember is that co-moving simply means that your let's say tau variable, the time variable is parallel, this d tau vector field is parallel to the velocity vector field. So you're sort of using a natural vector field in the problem to formulate this. And then you can write this down, okay? Don't feel compelled to understand each of these equations, but having written down the system, you can sort of convince yourself that this resembles kind of the continuity equation, and this resembles sort of the, let's say, the momentum equation in this language. Okay, so the theorem is that for small values of epsilon, there exists an imploding solution to that system of equations. And we refer to it as the relativistic Larsen-Penstone solution. In fact, Orient-Piran referred to it like that first. And it's sort of interesting. It features a sonic line, which is the boundary of the backward sound cone. And its maximal analytic extension of the self-similar thing is sort of stops, it's arrested here. So this is where the first singularity is triggered, and then it sort of extends into this so-called massive singularity, okay? So it's a terminating singularity. You could ask me, what can I tell you about the causal structure of this thing? And so this is bad drawing. This sonic line is far in, sort of by relative to the backward light cone. So there exists these smooth backward light cones, and then there exists kind of a first outgoing null geodesic, which also happens to be a line of similarity of this PDE. There exists the first such thing and the last such object. Okay, and they sit here like that. If you're discussing things like the maximal analytic extension, this is roughly speaking the structure of this space-time. And I mentioned to you that these objects, due to fat tails, are generically not asymptotically flat. So if you want to actually convince yourself that this is a naked singularity, you have to worry about asymptotic flatness, and this can be done. So you can modify the solution in the asymptotic region so that locally around here, it exhibits the exact, more or less looks like this, and then further out, it's just asymptotically flat. So you can modify it. This is not very difficult to believe by finite speed of propagation. Okay. If you want to know about proof ideas, let's discuss them later. Okay, so these are the existence results. And now in the last 10 minutes, I want to say something about the stability claim that I made. Now, if you remember, the stability claim was made for the Larsen-Penstone solution, which is the solution to the Euler-Poisson system when gamma is 1, okay? So the claim is that this solution is non-linearly stable against radial perturbations. So remember, this features a sonic point, and in a nutshell, you have to understand to what extent what features of the background steady state are relevant for this stability analysis. So already in the work of Merrill, Raphael, Sheftel, and Rodnyansky and Sheftel, it was clear that certain features of the background profile will stabilize the flow at high frequencies, okay? And that feature carries over. In pretty much any implosion setting, you always have that feature. They like to call it repulsivity. Now, before them, a similar feature was already exploited in semi-linear context. There's a lot of work on this, and this is by no means, this is sort of a beginning of a much larger list, but these sort of repulsivity properties have been important. But like I said, in semi-linear context, the problems we are dealing with are quasi-linear, so you have to worry about the location of the background cone. So to reiterate this point, the strategy of these four authors is quite robust, and it relies on ideas of so-called maximal accretivity and understanding the K properties of this semi-group, which is associated with a linearized problem. In their work in particular, if you look at it, they obtain some sort of semi-group decay. I'll explain in sort of what setting in a region which is sort of just slightly outside the backward sound cone. You might ask, what is the number of possible unstable directions? And that is in principle not known, but there is a sort of convincing numerical evidence that the solutions constructed by the four authors are indeed unstable. Okay. In fact, this numerical work suggests that it's unstable to shock formation. Okay. So what is our approach? So there's a couple of things. Some of them are technical, some of them are more conceptual. But we use Lagrangian coordinates, not only because we like to use Lagrangian coordinates, but it turns out it actually makes part of the discussion, it streamlines it in a much more efficient way. Did I do that? So we use Lagrangian coordinates. And this discussion of accretivity that I just mentioned, which has to do with the semi-group decay properties in backward light cones, actually, because of the monotonicity properties of this steady state of the Larsen-Penstone profile, they can be proved in arbitrary backward cones. So this cone can be fixed to be as sort of wide as you want. So that plays a role because, again, it simplifies the way you think about stability. But the crucial bit of the problem is to then actually show that the codimension is genuinely zero. And that boils down to the problem that is known as the mode stability problem. So I'll talk about this, but to kill the suspense, I'll tell you that we do at some point rely on interval arithmetic, sort of computer-assisted tools to handle this part. And finally, for reasons that are not terribly mysterious, we do have to sort of couple high and low energy spaces. So a lot of derivatives and somewhat less derivatives in order to make this work, because this is very believable, semi-group properties insist on using things like Duhamel formulation, which tend to forget about the quasi-linear features of the problem. Okay, so you can't just hope to close the estimates using simply semi-group decay. So you typically couple it to sort of energy type estimates at higher orders of regularity. And the two things have to talk to each other in the right way. Oh, I got 3 minutes. So what's the deal with this Lagrangian approach to stability? Well, Lagrangian coordinates simply means that you're looking at the flow map defined by the velocity field in the problem. And if you honor the symmetries of the problem, it simply means changing variables in the correct way. You will arrive at some sort of wave equation for the rescaled flow map zeta. If you do this and you kill off S dependence, what remains is a steady state of this problem, which we know it exists. It is actually the Larsen-Penstone solution. So this is the point of self-similar change of variables. Okay. And also it features an awkward term here that can change sign depending on whether you are to the left or to the right of the backward sound cone. So LP solution is now a steady state, and you have to describe it in the Lagrangian framework. two things that we can prove, it's not explicit, it's in fact very non-explicit, is that on approach to origin, it looks like z to the 1/3. The 1/3 reflects the value of the velocity at the origin. And on approach to infinity, it looks like z. So now you perturb around this thing. You consider some sort of perturbation. And when you spend some time thinking about it, you arrive at a sort of suitable first order formulation, okay? Which abstractly is written like linear plus nonlinear bit. So accretivity, I mentioned, we can actually show in arbitrary backward light cones, which is to say that we can show that the semigroup decays, in fact, exponentially fast. Okay? You fix a cone, and then you prove a statement like this. So the constant c depends on the cone, on the z node. And this is only true modulo finite number of directions, which is to say that coercivity, sorry, this is sort of a mechanism that is already was well understood in the semilinear world, modulo some compact perturbation or relatively compact perturbation, you actually have this type of decay. The whole point of this problem is to show that this finite number of directions is 0, okay? Which is very much tied to the proof of so-called mode stability. So this is what I'm getting at. There is always one unstable direction, which has to do with the time translation, but this is a fake instability. You have to take it into account through modulation theory, because you can blow up at time 1, at time 0, and at time 0 plus delta. And by a very simple sort of argument, you can also show that there can be growing modes when the real part is bigger than 1. So the question is, can we prove there are no growing modes when the real part is between 0 and 1? And if we can, then you can sort of hope to run a stability argument. Let me show it to you. You know, let's just flash it. I guess the blue bit cut it off. What I'm trying to highlight here is not so much the formula, but the fact that this is a highly non-self-adjoint operator. Okay, it's nasty from that point of view. And these coefficients, these are the Larsen-Penston solutions. They are sourcing the coefficients of the operator. They are not explicit. They are given as solution of some sort of ODE. Okay. Oh, sorry. Go forward, press go back. Okay. So this is a difficult problem, and the proposition states operator L is in fact mode stable, but we do rely at some point on computer-assisted techniques. There's a beautiful technique. Oh, did somebody ask a question? There's a beautiful technique by Glogic that allows you to prove mode stability for a number of sort of explicit self-similar solutions, which arise in typically in these semilinear contexts, but it doesn't work here, precisely because the coefficients are not explicit, and you need to know a lot about the coefficients. So to conclude, let me just tell you this. It's kind of a divide and conquer strategy. And when you do computer-assisted stuff, typically there's a part of the proof that you actually don't really understand. It just works. So the part of the proof that we truly understand is what happens at low and at high frequencies. So B naught and B1 are some cutoff numbers. It end up being something like 1/12 and then 8 maybe, or something like that. So in these ranges, when the imaginary part is small or big, what ends up happening, you're using a high order energy method of some kind for this elliptic eigenvalue problem. And as you go higher in energy, you're gaining better and better signs. And that's what makes it work. So this would have worked even if somebody forced you, you could have done it without the interval arithmetic. And in this intermediate region, this is where we really fundamentally rely on sort of a contradiction argument where we assume the solution exists and then check various sort of compatibility conditions for the solution to come from the left and the right, or within the sonic cone, and reach and check that they are not compatible using rigorous computer-assisted techniques. So I think I'll stop there because, okay, thank you.